It's done that. Okay, so y'all said number 5, worksheet. Okay. And then I'll pause it. All right, so number 5. Okay. All right, we got a horizontal surface on which the object slides is frictionless. So you always draw it, and you've got 3 objects, and they're connected by a steel cable or a rope or whatever, a bar, whatever you want to call it. And if the mass, if M, and of course this one's M, and that's 2M, and this is 2M, and we're pulling it in that direction. And if M is 2 kilograms, the tension in string 1 is 12 newtons. Okay, so we've got string 2, string 1. Determine F in newtons. So we want to find this right here. We want to find the force in the final cable here, okay? All right, so the tension F in 1 is 12 newtons, okay? All right. Now, if you want to, you can label these this way. You can say A, B, and C. Label them like that. And you know from Newton's second law that the F in 1, the force in 1, has to be equal to the force in A plus the force in B. Okay, it has to be, because we're pulling 2 objects here. Cable 1 is pulling 2 blocks. All right, so we know that. And we know the force in 1, okay? Now, understand something. These are all connected by a cable, okay? So whatever the acceleration of this block is the acceleration of this block, and has to be the acceleration of this block, okay? All this is telling us right here is how much tension is right there. That's all it's telling us, okay? So these are all moving at the same acceleration. They have to be. This is just like problem 6, except they're not hooked up with cables. I mean, 6 is just touching. It doesn't change anything, really, okay? All right. So we need to find the acceleration, don't we? Because we know, we know the sum of the forces is equal to what? It has to be equal to MA. Okay, and you say, well, how do you know that? Because you have a force here, and we want to find the force here. Well, that means there's got to be a net force. Okay, because it tells us they're sliding. Okay, there has to be a net force, because if there wasn't, it wouldn't be sliding. Okay, they'd just be sitting there. All right. And of course, we didn't draw our coordinate system, did we? But you know, on a problem like that, it ought to be obvious that it's normal coordinate system. Okay, because it's not tilted. All right. All right. So how do we find then the acceleration of these blocks? We've got to find the acceleration. How would we do that? Well, we know the force here, don't we? All right. Could we find the acceleration of these 2 blocks? Okay. Well, we could, couldn't we? Because remember, that is the net force right here on that cable. So this block is what? 2 kilograms? And because it's, remember, M is 2K, and so 2M would be 4 kilograms, and this one would be 4 kilograms, wouldn't it? Okay. All right. Does everybody see where I'm going? So we know Newton's second law, F's equal to ma. There it is, y'all. F over m. And by the way, that would be the m of A plus the m of B. Right? So we just say 12 newtons divided by what? 6 kilograms? We get 2 meters per second squared. Okay. Now it's just plain old Newton's second law. Okay, so how do we find the force total? Or you could call that the force in cable 3, or force in cable 0, or whatever. Okay. All right, well, how are we going to find that? Well, F's equal to MA. So it's all add up all the masses. So we got, and that's mass total. It has to be, because you got a mass here, here, and here, and there's where we're pulling. So we got what? 2 plus 4 plus 4 times acceleration, which is 2 meters per second squared. And we get what? 20 newtons? Does that make sense? Does that make physical sense? Okay. See, they gave us a force. When they give you a force, now remember, and you say, well, we didn't call that a net force, y'all. It has to be a net force. And you say, well, how do you know? Because it's sliding. It's moving. Okay? If the object has a force applied to it and it's moving, sliding, there has to be a net force. It has to be accelerating. That's just one of those things, conceptual things. You got to remember, oh yeah, if it's at equilibrium, there's no net force. The net force is 0. If it's not at equilibrium, the net force is equal to MA. That's just one of those conceptual things that you got to get in your head, okay? All right? Put it on your note card if you have to write it that way. I don't care. Be fine on your formula card. Okay? All right? Does that make sense now? Do you see how we got that? Okay? I mean, it's really just like 6. It's just that it gave us a force in the middle instead of on the ends. Well, it doesn't change anything. Okay. Number 6, it gave us the forces on the ends. We still had to find a net force. We had an 18 and a 6, and they were opposite directions. Well, you just get the net force, which is 12. Okay. All right. Any questions on that? Okay. Now you're going to have a problem on your exam like either 5 or 6, similar to it. Okay. More than likely. Okay, so you go ahead and just put a check mark. All right. All right. All right. Do you want me to go to chapter 4? Didn't we work one? We worked one in chapter 4, didn't we? Chapter 4, didn't I work one? I can't remember. Part of number 1? Okay, let's look at that. Yeah, because it seemed like we ran out of time. It's number 1? Yeah, okay. Yeah, it's from old videos too, yeah. All right. Yeah, let's because what was the second part? Did we not answer the second part? All right. Yeah, find the magnitude and the resultant force of the angle as it makes, yeah, that you just do arctan. You have to do the square root of the squares to find the magnitude, and then you do arctangent to find the angle. Okay, what about, what about number, that's just a conceptual there. What about number 16? That one's pretty easy though. That's a ratio problem. That's where you're just setting it up as a ratio. That's all that is. Number 11? Yeah, I was going to say let's look at number 11. Yeah, that one's a little bit lengthy. And then we'll look at one maybe in chapter 1 or 2 in chapter 5. Is it hot in here to y'all? It's kind of humid down here. Okay, so this is chapter 4, page 124. All right, let's look at it. Okay, a hockey puck with a mass. So we got a hockey puck. All right. And it has a mass of 0.16 kilograms, okay? Is at rest at the origin. All right, now it's very important. It's at the origin, x initial, 0 meters. It's at rest, v initial, 0 meters per second. Very important you write all this down as you go, okay? All right. It's a horizontal frictionless surface, so it's frictionless, You could write that down if you wanted to. Of the rink. At time t equals 0, a player applies a force. So we say at time 0 seconds, we have a force of 0.25 newtons applied to the puck. And it's parallel to the x-axis, so here's the force. Okay, and if you want to draw the person standing here and he hits it with his hockey stick, okay, all right. And this force is applied until time is equal to 2 seconds. So the force is applied for a 2-second interval. All right, let's look at it in parts, okay? A, what are the position and speed of the puck at time equals 2 seconds? So we want to know the final displacement, at the final displacement at 2 seconds, right? X final at 2 seconds. Okay, let's go ahead and do a few other things. Let's establish our axis. Well, you know it's going to be that way. Y and X. I mean, come on, it's a flat surface. And what else do we need to write? What are the sum of the forces? All right, is it equal to 0 or is it equal to MA? I heard somebody say it, mumble it. MA, very good. And you say, how do you know that? Because a force is applied for 2 seconds. Look, y'all, when a force is applied, it's accelerating. It's not at equilibrium. Now, had it said the object is at equilibrium or the object has constant speed, then we would have known that the forces were at equilibrium. See, those are words you got to watch and look for, okay? And again, that's one of these conceptual things you just have to wrap it around your brain, okay? Okay? You have to always ask yourself these questions. Is it accelerating or is it constant speed? If it's constant speed, it's not accelerating. Okay. So we've established that. Okay. Now, if you remember your kinematic equations, oh dear Lord, yeah, we're not going to get away from them. Sorry, we're just not. You remember there were, every one of those equations except for one had acceleration in it, didn't it? And one of them was x final is equal to 1/2 v initial plus v final times the time, right? Okay. Well, we don't know v final, and we know v initial, but we don't know v final, so we can't use that one. So the other three have acceleration. So what does that mean we got to find? We got to find acceleration. Okay? Do you see how I went through that process of determining which equation? We got to find final displacement. All right, there are 3 equations that have displacement in it. Okay? Am I right? Or 2 equations? 3. There's 3. There's 3. Okay? Well, there's really only one that's going to fit because we don't have a final velocity, do we? We don't have final velocity. All right, so we can't use the v squared final is equal to v initial squared. Can't use that one. Okay, can't use one I just told you. So the only one left is which one? Yep. That one right there. Do you see how I did that by process of elimination? Okay. We don't have a final velocity yet. So we can't use the other 2. So the only one that'll work is this one. We have all this information right here. Okay? All right. So we want to find final displacement. All right, we'll plug it in. Initial was 0. Initial velocity was 0 times 2 seconds plus 1/2. All right, now we got to find acceleration, don't we? How do we find acceleration? Well, it told us the force is this and the mass is that. Right there, y'all. Newton's second law. At 1.56, thanks. Okay? Does that make sense? Now we can plug that in. Times 2 seconds. And what do we get for a final displacement? 3.12 meters? Is that right? Whoop, squared. There we go. Or did I give you the wrong? No, I'm looking at the... That's right, isn't it? 3.12? Let me do it right. So we got 4 times 1.56 times 0.5. 3.12. Right? Okay. Okay, so there's our displacement. Now what's the rest of the question asked? What are the position and speed? Speed. Okay? All right, so we got to find the speed now, don't we? All right, we know an acceleration. Here's our acceleration right there. We know our time right there. All right? So what equation, and there are 2, but let's use the easiest one. Why not? Let's use the easiest one. So that's 0 plus 1.56 meters per second squared times 2 seconds. And what do we get? Well, what do you know? 3.12 meters per second. Right? Okay. Now, could we have used the other one? Yeah, it should work too. But we don't have to square on this one. Okay? We don't have to square. All right? Okay, now this problem is in chunks. All right? Okay, let's look at the next part. Did everybody see how I got that? I didn't pull a rabbit out of the hat. Go back to those kinematics. You always use your easiest equations. I mean, if you can use one that doesn't have a square in it, use it. All right? But sometimes you may not have any other choice. All right?
Can I ask a question?
Sure.
When I've done this, I've done it for a total of 4 seconds instead of 2. You have the first 2 seconds, and then you have 2 seconds in between 5 and 7.
Yeah, we're getting to that. But it wanted it on the first leg.
Okay, all right.
Isn't that what it asked?
Because I just doubled,
Yeah.
my answer was 6.25
Okay. For
for a total of 4 seconds of travel.
yeah. Okay, that's true. That's correct for a total of 4. But didn't it ask, let me make sure I read it right, what are the position speed after 2 seconds or at 2 seconds? Part A. Yeah, that's part B. You're looking at part B. Yeah, you're looking at part B. Which you're right. That's the correct answer. Okay. All right, so now let's look at 11B. All right. Now look at 11B. If the same force is again applied at 5 seconds. All right. Okay, so let's think about this. All right, so we go from 0 to 2 with a force, and then we go from 2 to 5 with no force, right? Is that correct?
Yeah.
So part B there is what? Acceleration is equal to, it's traveling with constant speed, 0 meters per second. Right? Squared. No acceleration from 2 seconds to 5 seconds. Okay? But then at time 5 seconds, this force is applied again, isn't it? Until 7 seconds. So from 5 seconds to 7 seconds, we have a force again of 0.25 newtons. Okay. All right. Then it's asking us what? What are the position and speed at 7 seconds, right? So we're wanting to know what it is at 7 seconds. So we've got to find x final at 7 seconds and v final at 7 seconds, right? Both of those. Okay. All right. Okay. Now, to be able to find this one right here, we've got to find the displacement during that 3-second interval, right? Yes? All right, so what was it? X final at 2 seconds is equal to what? X initial, right? Okay. X initial at what? 3 seconds or 2 seconds? From 2 seconds to 5 seconds is what? 3.12 meters, right? So in other words, the puck, draw it. The puck is here, all right, at time 0. 2 seconds later, it's here, all right, 2 seconds. The displacement is 3.12 meters from there to there. Okay, so that means at this point, the initial displacement becomes 3 meters for this next leg of time. 3.12 meters. All right? Okay. Okay? All right. So, since this is moving with constant speed, all right, so from here to here, all right, draw it now. This is at 5 seconds. Time's equal to 5 seconds. We were moving at what? Constant speed. Right? All right, so how do we find the displacement? This is easy. All right, velocity average, because look, if it's moving at constant speed, the average velocity is going to be the same throughout. Is equal to what? Change in x over what? Change in time. So change in x is equal to what? The velocity average times the time. Okay? All right. So what is our velocity average? Okay. We know the displacement at that point, but now wait a minute. What was the speed right here at the end of the 2-second leg? The velocity was what? 3.12 meters per second, wasn't it? So that means from here to here, the speed is what? From there to there, during that time frame, 3 seconds, if it's moving at constant speed, it has to be 3.12 meters per second. So, 3.12 meters per second times what? 3 seconds? Because from 2 to 5 is 3 seconds, right? And we get what? 9.36 meters, right? All right, but now that's from here to here. We're wanting to start right here. We're wanting to know what the displacement is from here to there. All right, it's 9.36 here, it's 3.12 there. So the x initial at 5 seconds is equal to what? 12.48 meters. So that means right here, the initial displacement is 12.48 meters, right there, at time 5 seconds. And we're going to go to 7, aren't we? Times 7 seconds. Okay? Now let me ask you something. Is the acceleration the same throughout all this motion? Because remember, at 5 seconds, we hit it again with the same force. Well, if the acceleration was 1.56 meters per second squared here, then from here to here, the acceleration is what? 1.56 meters per second squared, right? Same force, same acceleration. Same size puck. All right? Now let's find the final displacement at 7 seconds. So what would that be? Okay. Are you watching? All right, what's my initial displacement at 5 seconds? Remember, you got to add both of them together. So we found it here. It was 3.12 meters here, 9.36 here. Okay? All right? So it was what? 12.48? I got it right there. 12.48 meters. All right, plus. All right, now, what is going to be my initial velocity? Okay, y'all, it moved at constant speed till it got right here at 5 seconds. Well, it was whatever my constant speed was, 3.12 meters per second, right? And what's the time interval? From 5 to 7 is 2 seconds, plus 1/2, the acceleration is 1.56 meters per second squared, times 2 seconds squared. And what do you get? 21.84 meters. Now this is a little bit involved. But again, y'all, you have to remember, oh yeah, we got a force, and then for 2 seconds we got constant speed, and then we want to know what it is for the last 2 seconds. But you got to realize it's displacing through all that first 5 seconds. You got to find out what the displacement is. Okay? All right. Did everybody see I got 21.84? All right. Okay, y'all. How do we find final velocity on the last problem? Remember, I said do it the easy way. Can I flip it? All right. I'll go back if you need me to. So final velocity is equal to what? Initial velocity plus AT. All right, y'all. What was the initial velocity at 5 seconds? Remember, it's moving with constant speed. Remember, at the end of 2 seconds, it's 3.12, and then it travels at that same speed until 5 seconds. Okay? 3.12 meters per second plus 1.56 meters per second squared times 2 seconds, and you get a final velocity of what? 6.24 meters per second? Okay? And that is at 7 seconds. If you want to label it that way, which doesn't hurt. So we do it in chunks. Okay? All right. I mean, there's really no way to plug in you can't do this one in one calculation. You know. I mean, I say you can't. You could, but it'd be one heck of an equation. You'd start taking an equation and substituting in, and it would be like this long. I don't like doing that. You're prone to make a mistake, I think. But now you may like doing it that way, and if you want to do it that way, do it that way. You don't have to work them the way I work them, for crying out loud. Okay? All right. Does everybody see how we come to that conclusion? Okay? All right. Y'all want to look at one in chapter 5? There's not any questions? I'll admit, now that one's a little lengthy. That one's involved. Now, I can't give you 3 or 4 parts. I can't give you that many parts on a test problem. It'd take too long. I mean, you might do the first part and that's it. Yes? Chapter 5? Is that one of those that makes us want to go cry? Might be. They all make you want to cry, don't they? Yeah, they have a tendency to do that sometimes. Oh, yeah, okay. Okay. All right, so we got a small model car with mass M, travels at a constant speed on the inside of a track, and the figures listed there, they show you what it looks like, of radius 5 meters. So this is number 47, let me label it, chapter 5, page 163, okay? All right, so let's draw it. So we draw it, and the radius is 5 meters, right? Radius 5 meters. And we got a little car. Okay, if you want to draw the car, it wouldn't hurt. Draw it. Close enough. All right. Okay. And of course, it's going to duplicate itself up at the top. If you want to draw an arrow up there, you can. And it travels at a constant speed, but now it's going in a circle. So even though the speed is constant, is it accelerating? Yes. Because it's going in a circle, uniform circular motion. So the sum of the forces then are going to equal to what? It's moving in a circle, so it has to be MA, centripetal force here, okay? Centripetal force. Now see here again, y'all, this is conceptual stuff. This is not the formula. This is, oh yeah, what principle of physics is being applied here? And this is constant. You say, how do you know it's uniform circular motion? Because it said it was moving with constant speed. So that means it is uniform circular. So this don't have nothing to do with formulas. Motion. This is conceptual stuff. Okay? Uniform circular motion, you're going to have acceleration. Period. That's why when you go, if you're on a merry-go-round, you're accelerating. Even though it's moving at constant speed, you can feel the acceleration, especially if you're sitting on the outside. Now, if you're sitting towards the inside, it's not quite as bad. But if you're sitting out there on the outside, yeah, you can tell it. Okay? All right. Okay. All right, but it's still uniform circular motion. All right. Okay? And why does it change? Because the radius changes. If you move towards the middle, you're changing the radius. Okay. Okay? All right, so what are we doing here? Have we established that now? All right, it says radius 5 meters. If the normal force exerted by the track on the car when it is at the bottom of the track is equal to 2.5 mg. Okay? So then we're going to say then that right here, right there, the force normal, and if you want to write little n, okay, but that's the way I like to write it, is 2.5 mass times g. Okay, how much time does it take for the car to complete one revolution around the track? That is period. So T is what we're looking for. The time it takes to complete one cycle is period. The number of cycles in a time interval is frequency. Please don't confuse the two. It's easy to do because one is the reciprocal of the other. All right? The number of cycles in a second is frequency. The number, how long it takes to complete one cycle is period. They're the reciprocal of each other. All right. T is equal to 1 over F, and F is equal to 1 over T. Big T, period. All right? Okay. Okay. All right. We remember from these equations right here that acceleration is equal to 4 pi squared r over t squared. You remember that equation? And where does that come from? Well, that comes from this equation. This comes from A is equal to v squared over v squared over r. Excuse me. Yeah. Right? And where does all that Greek arithmetic come from? And I like the Greeks. Thank God for them. That comes from the velocity of an object going in a circle. Okay? 2 pi. Remember that equation? Okay. All right. Okay? Was it 2 pi r over t? Yeah, I believe it was. 2 pi r over t? Okay. All right. Then you square it, and you get that. Okay? Because we're squaring velocity. All right, all right, all right. Okay. But I just want you to know where it's coming from. I'm not just pulling it out of the thin air. All right? Now, okay. All right, so we know that centripetal force is this right here, isn't it? mv squared over r, right? And if you want to put the mass in parentheses, you can. Okay? So, what are we going to do here? We're going to have to do some substitutions, aren't we? Here in just a minute. All right, now it's asking what? Let me read it again. It says, how much time does it take to complete one revolution? All right, so if the normal force here is 2.5 mg, let me ask you this. Is that going to be the same at the top? No. Okay. All right. Now we're missing something again here, aren't we? We don't have a velocity, but we can find acceleration. But we've got to determine what the acceleration is, don't we? All right, we're still not through writing our equations. All right, so let's write an equation for this motion right here. Okay? Because here it's 2.5 g. Well, what is it up here? All right, so we got 2.5 mg minus what? Mg? Because remember, the centripetal force here is what? That way, isn't it? What is the force here? Now remember, this is the normal force. So that right there is the normal force, isn't it? Right? Which is equal to ma. And A then becomes what? All right, well, y'all look. The masses cancel out. You've got 2.5 minus 1 mg leaves me 1.5 mg divided by m, and so we are left with what? 1.5 g. And so that is my acceleration. Okay? And you say, well, why are you doing that? Well, you're going to find out. You've got to find the acceleration. Because why? Because look, we got to find the period. See right there? See here, I don't know the velocity. All right? So when we solve this equation for period, what does it become? It becomes the square root of 4 pi squared r over a, all under the radical. Okay? Solve this equation right here for period. Does everybody see how I got that? See, we had to determine, because we remember now, look, we determined that it was accelerating. The normal force is this way, mg is that way. All right? And that normal force is created from centripetal acceleration. All right, so let's plug everything in. So we got what? We've got 4 times pi squared times 5 meters divided by 1.5 times 9.8 meters per second squared. And we should get 3.66 seconds. Now this one's pretty involved. This one's kind of involved too. Okay? All right? Does everybody see how I came to that? Now look, you say, well, wait a minute, where's the centripetal acceleration? Right there. It's pointing towards the center of the circle. Okay. All right. What's pulling down? Mg. All right. And so all throughout that circle, all throughout that motion, it's going to travel at 1.5 times g. All because it's uniform now. Don't forget, it's uniform. Okay. All right. So here again, y'all, I hope you have that equation on your formula card. You should. That's from last couple of chapters. Like chapter 3, I believe.
Did you get 1.5?
All right, right here. 2.5. All right, the force in this direction was 2.5 mg. We know that gravity's pulling down. That's mg. And we know it's accelerating. Okay? So 2.5 mg minus mg, because it's in the opposite direction, is equal to ma, and then solve for a. That's why you got to draw it, y'all. Draw it and label it. Okay? Because look, I know it said north. Now this is what throws you off. This is what throws you off. Because it calls out a normal force. Okay? Yeah, but look, which way is that normal force pointed? It's pointed towards the center of that circle, isn't it? So that becomes the what? Centripetal force. Okay? I know it threw you when it said normal force. That might have thrown you a little bit. But if you draw it and you put that force in there, then that, well, hey, that's centripetal force. Okay? And we know there's a force in the opposite direction, gravity. Okay? Because how do we define normal force? mg. So we got to find our acceleration. Boom. Okay. And then plug it in. I can't remember if I put that one on the exam or not. Or you might have that one on the exam, or one similar. So you might put a check mark by that. We'll look at this Wednesday. We'll look at this Wednesday. All right, any questions about how I come to that? Again, free body diagrams, draw and label. Okay, draw and label. Normal force, gravity, it's accelerating. We've already determined that. Okay, that's kind of like an elevator problem. Okay. It sets up similar. Just depends on which way the acceleration is occurring on the elevator. And by the way, that's another good test problem. And yes, I could put it on there, the elevator accelerating downward. And if it's accelerating downward, you're going to weigh what? Less. So if the person or the fish or whatever weighs 10 newtons, then you should weigh less than that going down. Okay. All right, any questions? All right. Unpause. And remind me to go back and show that problem that Lynn worked, okay? Is equal to MA. Okay. Can we solve it now? Now remember, that mass of the rocket, that is total mass. It told you the box, the electrical box, everything. It's the total mass. Okay? Don't let this right here throw you. Don't let that right there throw you. We'll get to that on the next part. Okay? So your acceleration ends up equaling what? So the acceleration is equal to F thrust minus mg divided by what? The mass of the rocket. Right? Okay. All right, now look at part B. When the rocket initially accelerates, how hard does the floor push on the power supply? All right. Now remember, this right here is before acceleration. So the floor pushing, what force is that? Do I need to fill in this? This is part A. The answer was supposed to be, and I'm going to let you fill it in, 3.96 meters per second, 6 squared. All right, part B. All right. Okay, where's the normal force? Right there, Fn. All right, and we know it's doing what? In what direction? We know that there's weight, don't we? mg, and we know it's accelerating, right? Okay. So what are we looking for? We're actually looking for the normal force, aren't we? Let's write an equation. Force normal, all right, look, force normal is up. That's up. Weight is which way? Down. Y'all, I'm just going to tell you right now, weight's always going to be down. Always. Even if you're accelerating downward, weight is still down. Okay? I mean, y'all, come on. You don't weigh up. You don't jump on the scales and go up in the atmosphere when you weigh. It's pulling you down. Okay? All right. So it's equal to what? Minus mg is equal to ma, and so let's find force normal. And it's what? mg plus ma. Now, does that make physical sense? Will it weigh more? Going up. Well, do you weigh more when you go up in an elevator? Absolutely. That equation makes perfect physical sense. So again, I'm going to let y'all plug in the data and you work it out. 21.76 newtons. Okay? You plug it in. All right?
Can you factor out the M and just do M times plus A?
You can do, now say that again. Factor out an in.
Step above that.
Sorry. Well, you...
Apologize.
You can't... All right.
That's what I done, and I got the same answer.
Yeah. You can, yeah. Yeah, because you got G and you got A, factor out the M. Yeah, mm-hmm. Yeah, I didn't think to write it that way. Yeah, just M times G plus A. Now, by the way, how do I find the mass of that box? Well, now notice it gave us that right there. And weight is what? Equal to mg. So mass is equal to weight divided by g, so 15.5 newtons divided by 9.8 meters per second squared. And it should have been something like 1.58 kilograms. So see, we got to find the mass of the box. But it gave you the weight before it took off. Okay? I like that problem too. All right, any other questions? Okay. All right. So let's go home and bang our head. Hang on.